Humanity once lived under a sky of pure mystery. This is the story of 21 experiments that tore down that cosmic veil forever. By the end of this journey, you will understand exactly how a handful of daring questions reshaped our entire universe. We will uncover what a swinging pendulum in Paris revealed about our spinning world, and how a persistent, faint hiss from the depths of space rewrote our origin story. What do you believe it takes to overturn everything we think we know that pendulums swung with a steady, hypnotic rhythm? A heavy iron ball on a wire nearly 200 feet long. Léon Foucault had created more than a scientific instrument. He had built a cosmic clock. As it swung back and forth high inside the Paris Pantheon, its tip traced a line in a thin layer of sand spread on a circular platform below. To the audience watching, the pendulum seemed to maintain its plane of swing, a constant back and forth. Yet, as the hours passed, the line in the sand slowly, inexorably turned. The pendulum was not changing direction. The entire world was rotating beneath it. This was the first direct, physical proof that the ground we stand on is not a fixed stage but a spinning sphere. For centuries, thinkers had deduced the Earth's rotation by watching the complex dance of stars and planets. But here was evidence you could see with your own eyes. A silent, graceful demonstration that we are all living on a giant, rotating carousel. This single experiment in a Paris monument grounded a vast astronomical truth in the simple, tangible physics of a swinging ball, forever changing our visceral understanding of our place in the cosmos. If the very ground beneath our feet is in constant motion, what other fundamental truths about our universe are waiting to be revealed by a simple, clever experiment? The silent, spinning Earth revealed by Foucault's pendulum was just the beginning. Now, a new question emerged from the very substance of the cosmos. What fills the void between the stars? 19th century physicists were convinced space was not truly empty, but saturated with an invisible, frictionless medium they called the luminiferous ether. This mysterious substance was thought to be the necessary fabric through which light waves traveled, much like sound waves move through air. It was the defining backdrop of the universe, an absolute frame of reference for all motion. Then came Albert Michelson and Edward Morley with an exquisitely sensitive device designed to feel the ether's whisper. Their interferometer split a single beam of light, sending the two halves on perpendicular journeys along massive stone tables floating on a pool of mercury. The entire setup was isolated from the city's vibrations, a temple of precision built to detect an ethereal wind. The principle was straightforward. As Earth raced through the ether in its orbit around the Sun, one light beam should be traveling with this cosmic current, while the other moved across it. When the beams were recombined, this difference should have created a telltale interference pattern, a set of shimmering lines proving we were swimming through a cosmic sea. They meticulously rotated their apparatus, repeating the experiment at all hours and through all seasons, expecting to see that signature shift. They saw nothing. The light beams always returned in perfect sync. There was no ether wind, no drift, no evidence of the universal medium. It was a stunning non-result. The most elegant null result in scientific history shattered a foundational belief. There was no stationary sea of ether. The speed of light was not just fast, it was stubbornly, unchangeably constant, no matter how fast you yourself were moving. This baffling discovery forced physicists to abandon comfortable notions of absolute space and time, clearing the path for a young patent clerk named Albert Einstein. His theory of special relativity would rise from the ashes of the missing ether, revealing that space and time are not rigid and separate, but woven together into a single, flexible fabric. Sometimes, the universe's greatest secrets are not found in what we discover, but in what we fail to find. The universe had just thrown out the rulebook on space and time, and now it was about to rewrite the very nature of gravity itself. Einstein's general theory of relativity proposed a cosmos where gravity was not a mysterious force pulling at a distance, but a curvature, a bending of the very fabric of space and time around massive objects. It was a beautiful, radical idea, but was it real? The answer would come from a perilous journey to capture a few precious moments of darkness. In May of 1919, the physicist Arthur Eddington led 2 expeditions to the path of a total solar eclipse. One team braved the jungles of Sobral, Brazil, while Eddington himself journeyed to the island of Penzias off the coast of Africa. Their mission was audacious: to photograph the stars that would become visible in the daytime sky as the moon blotted out the sun. According to Einstein's theory, the sun's immense gravity should act like a lens, bending the light from those distant stars and making them appear slightly out of place. It was a tiny effect, a shift no greater than the width of a coin seen from a mile away, but it was measurable. On the day of the eclipse at Penzias, storm clouds threatened to ruin everything. As totality began, the sky darkened and the stars emerged, but Eddington and his team were frantically taking photographs through broken cloud cover. Back in the laboratory, when they developed the photographic plates and compared the star positions to their known locations at night, the data told a revolutionary story. The starlight had been deflected. The sun's gravity had indeed bent the path of the light, just as Einstein had predicted. This was not merely the discovery of a new fact, it was a new way of seeing the cosmos. Matter and energy told spacetime how to curve, and curved spacetime told matter how to move. Gravity was geometry. Eddington's confirmation catapulted Einstein from a brilliant physicist into a global icon, and it validated a framework that now explains the orbit of Mercury, guides our GPS satellites, and predicts the existence of black holes. A few minutes of celestial alignment, captured by brave scientists on a remote island, had proven that our universe is built on a malleable, dynamic stage. But if gravity can warp the path of light, what other invisible structures are hidden within the fabric of the cosmos, waiting for the right experiment to reveal their shape? The universe, it seemed, was not only curved but also in motion. While Einstein's equations had suggested a cosmos that might be breathing, it was a quiet, unassuming astronomer at Mount Wilson who would hear its first breath. Perched high above the smog of Los Angeles, Edwin Hubble peered through the most powerful telescope of its era, a 100-inch giant that served as a window to the depths of space. His target was a class of stars known as Cepheid variables, cosmic lighthouses whose rhythmic pulsing allowed him to measure distances with unprecedented precision. He was not just looking at stars, he was measuring a void. He found these pulsing beacons not within our own galaxy, but embedded within faint, swirling patches of light then called nebulae. His measurements were staggering. These nebulae were not nearby clouds of gas. They were entire other galaxies, island universes millions of light years away, floating in a vast and mostly empty ocean. The known universe had just expanded by an almost inconceivable degree, but Hubble was not finished. He then turned to the work of another astronomer, Vesto Slipher, who had painstakingly recorded the light from these distant galaxies. Slipher had found that the light from almost all of them was shifted toward the red end of the spectrum. This redshift was a familiar sign of motion, the same Doppler effect that makes a receding ambulance siren drop in pitch. The galaxies were racing away from us. When Hubble combined his own distance measurements with Slipher's velocity data, he uncovered a pattern of breathtaking simplicity and profound implication. The farther away a galaxy was, the faster it was receding. This relationship, now known as Hubble's law, painted a picture of a cosmos in a state of uniform expansion, like raisins in a rising loaf of bread, all moving apart as the dough itself expands. This was the final, shattering blow to the idea of a static, eternal universe. The cosmos was not simply existing, it was evolving. If everything is flying apart now, then rewinding the cosmic film implies a moment when it was all compressed into an unimaginably dense, hot point. Hubble's discovery was the first direct observational evidence for the event we now call the Big Bang, the explosive origin of everything we see. A man with a telescope had not merely found new objects in the sky, he had found the story of the sky itself, a narrative of a universe with a definite beginning and a fate tied to its initial explosive birth. If the entire cosmos is stretching like the surface of a balloon, what does that tell us about its ultimate fate and our own place within its expanding history? The grand expansion of the universe discovered by Hubble was a breathtaking idea, but it was still missing its final, tangible proof. That proof arrived not from a mountaintop observatory, but by accident, through a persistent, maddening hiss. At Bell Labs in New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a massive, ultrasensitive horn antenna. Their goal was to study celestial radio waves, but their work was plagued by an unexplained noise, a constant, faint microwave signal that seemed to come from every direction in the sky, day and night. It was an uninvited guest in their data. They meticulously checked every possible source of interference. They pointed the antenna at New York City, thinking it might be urban radiation. They investigated if it was fallout from high-altitude nuclear tests. They even famously evicted a pair of pigeons that had nested in the giant horn, scrubbing away what they called a white dielectric material, convinced it was the source of the problem. Yet the hiss remained. It was a ghost in the machine that refused to be exorcised. This was not a technical flaw, it was a whisper from the dawn of time. Meanwhile, just a short distance away at Princeton University, a team of physicists led by Robert Dick had been actively building a detector to find this very signal. They had theorized that if the Big Bang were real, the entire universe should be filled with a faint, cool glow, the cooled-down remnant of that initial fireball, stretched by the universe's expansion over billions of years into the microwave part of the spectrum. When the two groups connected, the puzzle was solved in an instant. Penzias and Wilson had not found a defect in their antenna. They had stumbled upon the cosmic microwave background radiation. This was the afterglow of creation itself, a snapshot of the universe when it was just 380,000 years old, a time when it had cooled enough for light to finally travel freely. That faint hiss was the oldest light we can ever see, cooled to just 2.7 degrees above absolute zero. It was the definitive evidence that our universe began in a hot, dense state, a discovery that earned a Nobel Prize and transformed cosmology from a speculative field into a precise science. We could now study the infant universe's composition and structure, reading the faint imprints in this radiation like cosmic fingerprints. This was not just looking at the stars, it was listening to the echo of the universe's first cry. But if this echo was the final proof of our fiery beginning, what new questions did this ancient light hold within its faint, uniform glow? That ancient echo of creation was a whisper from the void, but humanity was already preparing to reach out and touch another world. Two robotic emissaries, Viking 1 and Viking 2, descended through the thin, rust-colored Martian atmosphere in the summer of 1976. Their mission was as audacious as it was direct, to perform the first-ever experiments designed to find life on another planet. These landers were not merely geological surveyors, they were interplanetary biologists, equipped with a miniature laboratory to interrogate the Martian soil. One of the most tantalizing tests was the labeled release experiment. A scoop of Martian soil was moistened with a nutrient soup rich in carbon-14, a slightly radioactive form of carbon. The idea was brilliantly simple. If Martian microbes were present and metabolically active, they would consume the nutrients and release gaseous waste products containing that telltale radioactive carbon. The instrument would then sniff the air above the soil, detecting this signature of biological activity. To the astonishment of the scientists, the experiment worked. Almost immediately, the instrument registered a significant release of radioactive gas. It was as if the soil itself had taken a breath. For a brief, electrifying moment, it seemed we had found life on Mars. But science demands more than a single positive signal. Other experiments delivered crushing ambiguity. A test searching for organic molecules, the fundamental building blocks of life as we know it, came back utterly blank. The soil appeared to be sterile. How could there be life without any organic material at all? The leading theory today suggests a fascinating, if disappointing, answer. The Martian soil is likely rich with powerful oxidizing chemicals, like peroxides. These compounds would have eagerly broken down the nutrient soup in a violent, non-biological reaction, creating the false positive, while simultaneously destroying any ancient organic compounds that might have been present. The Landers had not found life, but they had discovered a world far more chemically reactive and alien than anyone had imagined. Despite this profound ambiguity, the Viking missions were a monumental success. They gave us our first detailed look at the Martian surface, showing a rocky, windswept desert under a pink sky. They analyzed the atmosphere and measured the climate, painting a picture of a cold, dry world that may once have been warmer and wetter. They transformed Mars from a faint red dot in a telescope into a real place, a landscape of boulders and dunes that we could explore. The great Martian life debate they sparked continues to drive our exploration, pushing every subsequent rover and orbiter to look for more subtle signs, past or present, of a living world. Viking taught us that the search for life is not a simple yes or no question, but a complex puzzle where the very chemistry of a planet can play tricks on our instruments. If the soil of another world can so perfectly mimic the breath of life, how will we ever know for sure that we are truly alone? While Viking was searching the Martian soil for signs of life, the universe was sending out its own rhythmic signals from the depths of interstellar space. In 1967, a young graduate student named Jocelyn Bell Burnell was meticulously analyzing reams of paper chart data from a new radio telescope array. The instrument was designed to study the twinkling of distant quasars, but Bell noticed something peculiar, a faint, repeating signal that appeared and disappeared with the rotation of the Earth. It was a series of pulses, so precise and regular they seemed almost artificial. The signal arrived every 1.337 seconds with the unwavering accuracy of a cosmic metronome. The regularity was so uncanny that she and her supervisor, Anthony Hewish, half-jokingly labeled the source LGM-1 for Little Green Men. Could they have stumbled upon a beacon from an advanced extraterrestrial civilization? Further observations quickly ruled out that thrilling possibility. More of these pulsing objects were found scattered across the sky. They were not alien messages, but something almost as strange, the collapsed cores of massive stars that had died in violent supernova explosions. These were pulsars, or pulsating stars. A pulsar is a neutron star, a city-sized sphere of ultra-dense matter so compressed that a single teaspoon of it would weigh billions of tons. As this stellar cinder spins at incredible speeds, its powerful magnetic field acts like a cosmic lighthouse, funneling beams of intense radiation from its magnetic poles. If one of those beams sweeps across Earth, our telescopes register it as a pulse with every rotation. This was the first direct evidence for the existence of neutron stars, objects that had been theorized for decades but never before seen. They are the final, unimaginably dense corpses of suns much larger than our own. The discovery opened up an entirely new field of astronomy. Pulsars are not just cosmic curiosities, they are supremely useful tools. Their incredible rotational stability makes them the most accurate natural clocks in the universe, rivaling atomic timekeeping. By monitoring the subtle changes in the pulses from a pair of pulsars, Astronomers have provided some of the strongest tests for Einstein's theory of general relativity, confirming the existence of gravitational waves. They serve as navigational beacons for charting the structure of our galaxy, and the first exoplanets ever discovered were found orbiting a pulsar. All of this profound insight came from a graduate student's decision to investigate an anomaly others might have dismissed as mere interference. The story of pulsars is a powerful reminder that the universe's greatest discoveries often begin not with a grand answer, but with a persistent, puzzling signal that refuses to be ignored. If the spinning cores of dead stars can illuminate the fundamental laws of physics, what other secrets might be hidden in the faint, rhythmic whispers of the cosmos? Those rhythmic whispers from deep space were soon joined by the purposeful transmissions of two human-made travelers. The Voyager probes, launched in 1977, were built for an epic journey, a grand tour of the solar system's outer giants. Their mission was timed to take advantage of a rare geometric alignment of Jupiter, Saturn, Uranus, and Neptune, a celestial lineup that occurs only once every 176 years. This alignment allowed the twin spacecraft to use the gravity of each planet as a slingshot, hurling them onward to the next destination with incredible efficiency. They were our eyes and ears, sent on a one-way trip across billions of miles. What they found was a gallery of wonders that utterly transformed our picture of the outer solar system. At Jupiter, Voyager 1 discovered that the moon Io, a world roughly the size of our own moon, was a volcanic inferno. It was the first active volcanoes ever seen beyond Earth, with plumes of sulfur and silicate rock shooting hundreds of miles into space, painting the moon in brilliant yellows, oranges, and reds. This was a world being constantly remade from within, its interior heated and churned by the immense gravitational tug of war between Jupiter and its other large moons. At Saturn, the intricate ring system, which from Earth appeared as a few solid bands, was revealed in staggering complexity. The Voyagers showed us that the rings were made of countless individual moonlets, from dust grains to house-sized boulders, sculpted into braids, spokes, and waves by the gravity of tiny shepherd moons. The mission revealed that these gas giants were not just featureless balls of gas, but dynamic, storm-racked worlds. Jupiter's Great Red Spot was a colossal hurricane larger than Earth, and Saturn's North Pole held a mysterious, perfectly hexagonal jet stream, a geometric wonder defying simple explanation. The journey continued, with Voyager 2 pushing on to the ice giants, Uranus and Neptune. It showed Uranus as a tilted world rolling on its side, and found tenuous rings and a family of small moons. At Neptune, it discovered the fastest winds in the solar system, screaming across the blue planet at over 1,000 miles per hour. And on the moon Triton, it captured images of active geysers erupting nitrogen gas and dark dust into a thin atmosphere, a world so cold it was a geological surprise. The Voyager missions did more than just catalog new sights. They fundamentally changed our understanding of these distant realms. They showed that the moons of the gas giants were not dead, frozen rocks, but individual worlds with their own unique geology, hidden oceans, and the potential for habitats that could support life. They extended human perception across the gulf of space, turning points of light in a telescope into real, complex landscapes. These robotic explorers became our surrogates, proving that we could reach out, touch the unknown, and have it talk back to us. And as they completed their tour of the planets, they were given one final, timeless task: to venture into the true void between the stars. The faint hiss discovered by Penzias and Wilson was a monumental find, but it was also deeply puzzling. This cosmic microwave background was almost perfectly uniform, a smooth sea of radiation bathing the entire sky. If this was the blueprint for the universe, why was the cosmos so lumpy, filled with the grand structure of galaxies and vast empty voids? A map of this ancient light was needed, one sensitive enough to find the first tiny seeds of cosmic structure. That mapmaker arrived in 1989 in the form of the Cosmic Background Explorer, or COBE satellite. COBE was designed not just to listen to the universe's first cry, but to measure its exact temperature and listen for its faintest whispers. For 4 years, it scanned the entire sky, and what it found was a revelation. The background radiation was not perfectly smooth. Etched across the heavens were tiny variations, minute fluctuations in temperature no greater than 1 part in 100,000. These were the anisotropies, the cosmic fingerprints of the early universe. Imagine a perfectly still pond, and then spotting the tiniest of ripples on its surface. Those ripples are what would eventually grow, over billions of years, into the swirling currents and waves that shape the water. In the same way, these infinitesimal hot and cold spots in the cosmic microwave background were the gravitational seeds for everything we see today. The slightly denser, hotter regions held the potential to pull in more matter through gravity, eventually collapsing to form the first galaxies, stars, and planets. The less dense, cooler regions would become the great cosmic voids. COBE data was a perfect match for the predictions of the Big Bang Theory, providing a detailed baby picture of the cosmos when it was a mere 380,000 years old. This was not just a confirmation of our origin story. It was a transformation of cosmology into a precise science. For the first time, scientists could quantify the universe's initial conditions and trace its evolution with hard numbers. The COBE team, led by John Mather and George Smoot, earned a Nobel Prize for this work, which truly marked the dawn of precision cosmology. We now had a map of the primordial universe, a snapshot of its potential frozen in time. But if these tiny ripples were the seeds of all structure, what fundamental forces in the first fleeting moments of existence had planted them there in the first place? The deep, dark void between the stars is an illusion. In 1995, astronomers decided to test this idea with a seemingly reckless gamble. They pointed the most expensive and powerful telescope ever built, the Hubble Space Telescope, at a patch of sky near the Big Dipper that was considered profoundly empty. For 10 consecutive days, Hubble's giant eye remained locked on this single, dark point, collecting the faintest trickles of light across multiple wavelengths. It was a monumental investment of precious observing time with no guarantee of success. The resulting image, known as the Hubble Deep Field, did not just find a few faint smudges. It revealed a universe teeming with life, not biological life, but galactic life. Against the blackness of space, 3,000 galaxies glittered, a stunning crowd of spiral disks, glowing ellipticals, and chaotic, irregular shapes. This was not a simple photograph. It was a core sample drilled into the deepest layers of cosmic time. Each galaxy was a fossil from a different era, with the faintest, reddest specks of light representing some of the most distant objects ever seen, their light having traveled for over 12 billion years to reach us. We were seeing them not as they are today, but as they were when the universe was less than 1 billion years old, a mere infant. This galactic fossil record told a clear story of cosmic evolution. The most ancient galaxies were smaller, more fragmented, and wildly irregular, cosmic building blocks in the process of crashing together and merging to form the larger, majestic spirals and smooth ellipticals we see in the modern universe. The deep field confirmed that galaxy formation is not a singular event that happened long ago, but a continuous, dynamic process stretching across billions of years. It was visual proof that our own Milky Way has a history, emerging from a violent and crowded past. This single image transformed our understanding of cosmic history, moving it from theoretical models into a vivid, observable timeline. It demonstrated the unparalleled power of a telescope, freed from the distorting shimmer of Earth's atmosphere, able to peer so far back in time that it could almost witness the dawn of the first stars. If a random, empty patch of sky contains thousands of galaxies in every direction, how many more cosmic stories are written across the infinite canvas of the night? For centuries, our solar system stood alone, a singular example of planets circling a star. That profound isolation shattered in 1995 with a discovery that redefined our cosmic neighborhood. Two Swiss astronomers, Michel-Mayor and Didier Queloz, were not looking at planets directly, but listening for the subtle song of a star. They focused their telescope on 51 Pegasi, a sun-like star visible to the naked eye. Using a technique called the radial velocity method, they measured the star's light with exquisite precision, searching for a telltale wobble. The principle was elegant. A star and its planet both orbit a common center of mass. While the planet's tug is tiny, it causes the star to dance in a small, tight circle, a motion that imprints itself on the starlight. As the star moves slightly toward us, its light is compressed, shifting bluer. As it moves away, the light is stretched, shifting redder. This stellar wobble is incredibly subtle, a rhythmic drift in the color of starlight equivalent to a walking pace. What Mayor and Queloz found was astonishing. The data revealed a wobble with a period of just 4.2 days. This meant a giant planet, at least half the mass of Jupiter, was whipping around its star in an orbit tighter than Mercury's around our Sun. This world, named 51 Pegasi b, was a hot Jupiter, a type of planet completely unknown to our own solar system, a gas giant boiling in the extreme heat of a 4-day year. Its existence broke all our existing models of planet formation. The discovery proved that other stars had planets, and that those planets could be wildly different from anything we knew. It was the spark that ignited the modern hunt for exoplanets. This single detection opened the floodgates, leading to missions like Kepler, which stared at a single patch of sky to find planets by the dip in starlight they cause as they transit, and TESS, which now scans almost the entire sky. We have since found thousands of worlds, a menagerie of super-Earths, mini-Neptunes, and water worlds, revealing an astonishing diversity of planetary systems. Our own solar system, once the only model we had, is now just one arrangement in a galaxy overflowing with planets. The question is no longer if there are other worlds, but how many of them could be homes for life. The discovery of thousands of new worlds was a revolution in perspective, but a deeper, more fundamental mystery was brewing in the cosmic depths. The universe's grand expansion, revealed by Hubble, had long been assumed to be slowing down. The collective gravity of all the galaxies, stars, and dark matter was thought to be acting as a cosmic brake, gently pulling on the fabric of space and tempering its outward rush. The ultimate fate of the cosmos, a big crunch or a slow, cold fade, hinged on this delicate tug of war. To measure this deceleration, two independent teams of astronomers in the late 1990s turned to the most powerful cosmic explosions imaginable, Type 1, a supernova. These are not the deaths of massive stars, but the final, violent detonations of white dwarfs, the dense Earth-sized cores left behind by sun-like stars. When a white dwarf in a binary system siphons too much material from its companion, it crosses a critical mass threshold and explodes in a blast so uniform and so incredibly bright that it can outshine an entire galaxy. This consistency makes them perfect standard candles, celestial lighthouses of known intrinsic brightness. By carefully measuring how bright these supernovae appeared from Earth, astronomers could calculate their precise distance. And by measuring their redshift, they could determine how fast they were moving away from us. The plan was to compare supernovae from different epochs, looking for how much the expansion had slowed over billions of years. The results were not just surprising, they were paradigm-shattering. The distant, ancient supernovae were fainter than their redshifts predicted. This could only mean one thing: these stellar explosions were farther away than anyone had thought. The universe's expansion was not slowing down at all, it was speeding up. Some mysterious, repulsive force was overwhelming the pull of gravity, pushing galaxies apart at an ever-increasing rate. This discovery of an accelerating universe was so profound and so counterintuitive that the leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics. The mysterious agent causing this acceleration was given a name, dark energy. We do not know what it is. We only know what it does, and its effect is dominant, accounting for about 70% of the entire mass energy content of the cosmos. Combined with the invisible grip of dark matter, this means that over 95% of the universe is made of substances we cannot see and do not understand. The fate of the cosmos is no longer a graceful slowdown, but a runaway expansion, a future where galaxies will be torn away from each other into an endless, accelerating void. The ultimate destiny of everything had been rewritten by the faint, fading light of exploding stars. The accelerating universe was a breathtaking concept, but it was built on a foundation of profound uncertainty. We knew the cosmos was dominated by dark energy and dark matter, but how old was it exactly, and what was its precise recipe? The answers were hidden in the faint, mottled patterns of the cosmic microwave background, the afterglow of the Big Bang itself. The COBE satellite had given us our first blurry baby picture of the universe, but we needed a sharper, more detailed portrait. In 2001, the Wilkinson Microwave Anisotropy Probe, or WMAP, was launched to do just that. It traveled to a stable gravitational point 1 million miles from Earth, far from our planet's heat and radio noise, to listen to the whisper of creation with unparalleled clarity. For 9 years, its instruments scanned the entire sky, meticulously measuring the tiny temperature differences in the cosmic background radiation, those crucial wrinkles in spacetime that were the seeds of all cosmic structure. The map it produced was a revelation of precision. It was not just a confirmation of the Big Bang, it was a detailed cosmic biography. By analyzing the specific size and distribution of these hot and cold spots, scientists could extract the universe's fundamental parameters with stunning accuracy. WMAP revealed that our universe is 13.77 billion years old, a number known with a certainty of less than 1% error. It precisely quantified the cosmic budget, showing that the ordinary matter making up stars, planets, and us constitutes a mere 5% of the total. Dark matter, the invisible gravitational scaffolding for galaxies, makes up 27%, and the mysterious dark energy driving the cosmic acceleration dominates at 68%. Perhaps most profoundly, the data confirmed that the universe is geometrically flat on the largest scales. This means that parallel beams of light will never converge or diverge as they travel across the cosmos. A critical finding that tells us the overall density of the universe is perfectly balanced, poised between eternal expansion and gravitational collapse. WMAP transformed cosmology from a field of compelling theories into a science of exact numbers. It provided the consistent framework, the standard model of cosmology that now guides all our research. This single mission showed that by reading the subtle patterns in the oldest light, we could unlock the deepest secrets of the cosmos, from its explosive birth to its ultimate fate. If a map of ancient light can tell us the precise ingredients of everything that exists, what other fundamental truths are still encoded in the darkness, waiting for the right instrument to decipher them? Einstein's universe was not just a flexible stage, it was a dynamic one that could ripple and ring like a struck bell. For a century, his theory of general relativity had predicted the existence of gravitational waves, vibrations in the fabric of spacetime itself, sent out by accelerating masses. Yet these ripples were so fantastically tiny, so minuscule, that Einstein himself doubted we could ever detect them. They were a whisper lost in the cosmic noise. Then, on September 14, 2015, a whisper became a roar. At the twin LIGO observatories in Louisiana and Washington, a signal arrived. It was not a flash of light or a radio burst, but a subtle shudder in the very structure of reality. The laser interferometer gravitational wave observatories are perhaps the most sensitive measuring devices ever constructed. Each consists of two 4-kilometer-long arms arranged in an L shape. Inside these vacuum tubes, powerful laser beams race back and forth, bouncing between mirrors. In a perfectly still universe, the beams in each arm travel the exact same distance and return in perfect sync, canceling each other out. But if a gravitational wave passes through the Earth, it does something extraordinary. It literally stretches space in one direction and squeezes it in the perpendicular direction. For a fleeting moment, one arm becomes infinitesimally longer while the other becomes infinitesimally shorter. This change is almost impossibly small, a shift thousands of times smaller than the diameter of a single proton. Yet LIGO lasers registered it. The signal that day was a distinctive chirp, a rising frequency that swelled and then abruptly ceased. It was the sound of two black holes, each about 30 times the mass of our Sun, locked in a final, desperate dance over 1 billion light-years away. For millions of years, they had spiraled toward each other, and in the last frantic fraction of a second, they merged into a single, more massive black hole, converting a portion of their combined mass into pure energy that radiated outward as gravitational waves. This was not astronomy as we knew it. We were not observing light, we were listening to the vibrations of spacetime itself. This single detection opened an entirely new sense for exploring the cosmos, a sense of hearing. Suddenly, we could perceive the most violent and energetic events in the universe, collisions that are often completely dark to traditional telescopes. Since that first detection, LIGO and its European counterpart, Virgo, have listened to the mergers of more black holes and even a spectacular collision of two neutron stars, an event that also flared with light across the electromagnetic spectrum, allowing us to both see and hear the same cosmic cataclysm. We are no longer just stargazers. We have become eavesdroppers on the deepest rhythms of the universe. If we can now hear the invisible collisions of the most mysterious objects in existence, what other symphonies of spacetime are traveling through us, waiting for a sensitive enough ear to listen? Hearing the collisions of black holes was one thing, but seeing one was an entirely different challenge. This was not a matter of building a bigger telescope, but of building a telescope the size of the entire Earth. The target was the supermassive black hole at the heart of the galaxy Messier 87, a cosmic giant with the mass of 6.5 billion suns, located 55 million light-years away. To see its shadow against the bright, swirling gas of its accretion disk required a resolution so sharp it could spot a donut on the surface of the Moon. No single instrument could ever achieve this. The solution was as brilliant as it was complex. The Event Horizon Telescope collaboration did not build one telescope. They synchronized a global network of 8 existing radio observatories, from the high deserts of Chile to the volcanic peaks of Hawaii and the frozen plains of the South Pole. For a few precious days in April 2017, these far-flung dishes all turned to stare at the same point in the sky, their atomic clocks ticking in perfect unison. Each site recorded a torrent of raw data onto specialized hard drives, capturing the faint radio whispers from the edge of the abyss. This technique, called very long baseline interferometry, effectively created a single planet-sized virtual telescope. The resolution was unparalleled, but the data was not a picture. It was a puzzle of missing pieces. The hard drives, filled with petabytes of information, were physically flown to central processing facilities in Massachusetts and Germany. It took 2 years of meticulous work by hundreds of scientists to correlate the signals and assemble the fragments into a coherent image using sophisticated algorithms. The result, unveiled in April 2019, was an icon, a fiery, asymmetric ring of light, a cosmic hurricane of superheated gas circling at near light speed, encircling a central region of profound darkness, the black hole's shadow. This dark void was not the event horizon itself, but the silhouette it cast against the brilliant background, its light captured and trapped by the black hole's immense gravity. The image was a perfect match for the predictions of general relativity under such extreme conditions. It was direct, visual proof that black holes are not just theoretical phantoms, but real, physical objects that warp space-time and consume light. This single, blurry orange ring crowned a century of theoretical work and opened a new era of black hole astronomy. We are no longer just detecting their ripples or inferring their presence from stellar orbits. We are now looking directly into their dark hearts. If we can photograph a black hole in a galaxy 55 million light-years away, what other invisible monsters will we bring into focus next? The shadow of a distant black hole revealed an abyss, but much closer to home. Another machine was patiently reading a different story written in stone. On the surface of Mars, the Curiosity rover continues its slow, deliberate trek across the floor of Gale Crater. A robotic geologist on a mission to decipher an ancient planetary diary. Unlike the Viking Landers that tested for life itself, Curiosity was designed for a more nuanced quest, to determine if the red planet ever had the environmental ingredients to support life. Its drill is its primary tool, capable of hammering into Martian bedrock and feeding powdered rock into its onboard laboratory. Each sample is a time capsule, a page from a history billions of years old. The data that came back was unequivocal. Curiosity found complex organic molecules, the carbon-based building blocks of life, preserved in the mudstone of an ancient lakebed. This was not a fleeting signal, but a durable record. The rover was standing in what was once a vast body of water, a place where rivers once flowed into a lake that could have persisted for millions of years. This was a Mars utterly alien to the cold, dry desert we see today. A world with a thicker atmosphere, flowing water, and all the fundamental chemistry required for life to potentially begin. Beyond the ancient clues, Curiosity has become a long-term Martian weather station. It constantly monitors the surface radiation, crucial data for planning future human missions, and tracks the planet's seasons, from freezing winters to dust-choked summers. Its observations confirm that while the surface is hostile today, the subsurface environment could potentially harbor microbial life, protected from the harsh radiation. Curiosity transformed Mars from a simple object in the sky into a world with a rich and complex biography, a place that experienced a dramatic climate change on a planetary scale. It proved that the question of life on Mars is not a simple yes or no, but a deep investigation into a planet's lost potential. If an entire world can shift from being habitable to being a sterile desert, what does that say about the delicate balance that makes a planet a home? The faint cosmic whisper mapped by WMAP was a masterpiece, but it was still a sketch compared to the high-definition portrait that was to come. Launched in 2009, the Planck satellite was a technological marvel, designed to listen to the cosmic microwave background with such exquisite sensitivity that it could detect variations a million times fainter than the signal itself. For over 4 years, it scanned the entire sky from a vantage point a million miles away. Its instruments cooled to just a fraction of a degree above absolute zero, to hear the universe's first light without the static of its own heat. What it produced was the most precise map of the infant cosmos ever made, a detailed chart of its temperature and, for the first time, its polarization. These subtle patterns in the light's orientation are like the brushstrokes left by the universe's earliest moments, imprinted by the gravitational waves and density shocks of its violent birth. Planck's data refined the cosmic recipe with breathtaking precision. It told us the universe is 13.8 billion years old, sharpening our timeline. It confirmed with even greater certainty that ordinary matter makes up just under 5% of the cosmos, with dark matter comprising about 27% and dark energy about 68%. The numbers were now so precise they felt like fundamental constants of reality. But the most profound revelations came from the tiny anomalies, the slight asymmetries and unexpected cold spots that the standard model of cosmology could not fully explain. The data overwhelmingly supported the broad idea of cosmic inflation, that explosive faster-than-light expansion in the first fraction of a second that stretched the universe from subatomic size to a macroscopic scale, planting the seeds for all future structure. Yet, Planck's exquisite map also revealed features that are difficult for some of the simplest models of inflation to account for. It was as if we had finally gotten a perfectly clear photograph of a crime scene, only to find a few fingerprints that do not match any suspect. These anomalies are not errors, they are clues. They are pushing theorists to develop more complex and nuanced versions of inflationary theory, or to consider even more radical alternatives. Planck did not just confirm what we knew, it highlighted what we do not, proving that even our most successful models are incomplete. This satellite's legacy is a map of incredible certainty that, paradoxically, points directly toward profound new uncertainty. If our most detailed picture of the universe's birth contains features we cannot yet explain, what does that say about the very first moments of everything? Our galactic census began with a single, wobbling star, but it required a dedicated cosmic accountant to complete the tally. The Kepler Space Telescope, launched in 2009, was not designed to study a handful of stars, but to stare unblinkingly at a single, dense star field near the constellation Cygnus. Its mission was simple in concept but profound in scope: to monitor the brightness of over 150,000 stars simultaneously for years on end, watching for the faint, periodic dimming that occurs when a planet crosses in front of its star. This transit method is like detecting a gnat flying in front of a searchlight from thousands of miles away, a feat of precision that required Kepler to be one of the most stable cameras ever built. For 4 years, it gathered data, a silent sentinel recording the rhythmic winks of distant worlds. The flood of discoveries that followed was nothing short of revolutionary. Kepler did not just find a few new planets, it revealed a galaxy teeming with them. The mission discovered thousands of confirmed exoplanets and tens of thousands more candidates, a statistical treasure trove that allowed us to move from discovering individual worlds to understanding planetary demographics. For the first time, we could answer the question, how common is a world like ours? The answer was stunning. Kepler showed us that small, rocky planets, similar in size to Earth and Venus, are the most common type of planet in the Milky Way. It revealed that many stars host not just one world, but entire families of planets orbiting in compact systems, their years shorter than a single season on Earth. The most profound statistical conclusion was that planets vastly outnumber stars in our galaxy. Billions of suns are likely accompanied by billions of worlds. And of those, a significant fraction orbit within their star's habitable zone, that temperate band where temperatures could allow for liquid water to pool on a rocky surface. Kepler transformed our perspective from wondering if other Earths existed to knowing statistically that they must. It painted a picture of a galaxy where the ingredients for life are not rare, but could be commonplace, scattered across the starry expanse. The mission's legacy is a fundamental shift in our cosmic identity. We are no longer residents of a unique solar system, but of a galaxy overflowing with planetary real estate. Each distant wink of starlight, a potential new chapter in the story of life. If the galaxy is filled with so many Earth-like worlds, what does that mean for the silence that currently greets us from the stars? While Kepler revealed a galaxy filled with worlds, another probe was on a mission to touch our own star. The Parker Solar Probe is not merely observing the Sun from a safe distance, it is diving directly into its fiery atmosphere. Launched in 2018, this car-sized spacecraft was engineered to survive the impossible, a journey into the multimillion-degree corona, the Sun's outer atmosphere. To do this, it hides behind an advanced heat shield made of reinforced carbon composite, a technological marvel that keeps its instruments at room temperature, even as the front of the shield faces temperatures hot enough to melt iron. Its trajectory is a masterpiece of celestial mechanics, using a series of flybys of Venus to walk its orbit ever closer to the Sun, like a stone skipping across a gravitational pond to fall inward. Each close approach, or perihelion, sends it screaming through the corona at staggering speeds, making it the fastest human-made object in history. Within this inferno, the probe has uncovered bizarre and unexpected phenomena. It discovered sudden, dramatic flips in the Sun's magnetic field, structures scientists call switchbacks. These are like giant S-shaped kinks in the magnetic field lines that whip out from the Sun, releasing enormous energy and helping to accelerate the solar wind, the relentless stream of charged particles that flows from the Sun and bathes the entire solar system. Solving the mystery of the solar wind's acceleration is key to understanding a much older puzzle: why the corona is so impossibly hot. The visible surface of the Sun is about 10,000 degrees Fahrenheit, but the wispy corona that stretches millions of miles into space soars to over 1,000,000 degrees. It is as if the air around a flame were hundreds of times hotter than the flame itself. Parker's data suggests that these magnetic switchbacks in a process called magnetic reconnection, where field lines break and explosively reconnect, are dumping colossal energy into the corona, superheating it. This is not just abstract science. The solar wind and coronal mass ejections drive space weather, the storms in our cosmic neighborhood that can disrupt satellites, knock out power grids on Earth, and pose radiation risks to astronauts. By understanding the Sun's inner workings, the Parker Solar Probe is providing the data we need to better predict these solar storms, turning a celestial threat into a forecastable event. This mission proves that we can not only look at the stars but reach out and touch one, sending a piece of our curiosity into the heart of our solar system's furnace to read its magnetic pulse and listen to the solar wind being born. If we can now fly through the atmosphere of a star, what other seemingly impossible environments will we one day explore? The Parker Solar Probe was diving into the heart of our own star, but a new eye was opening to look back toward the very beginning of all stars. The James Webb Space Telescope unfolded its golden mirror far from Earth, a technological flower blooming in the void. Its mission was to see the unseeable, to capture the first starlight from the cosmic dawn. Unlike Hubble, which sees primarily invisible light, Webb is an infrared telescope, designed to detect the heat signatures of the most ancient objects in the cosmos. The light from the earliest galaxies has been stretched by the universe's expansion over billions of years, shifting it into the infrared part of the spectrum. Webb is a time machine, built to watch the first chapters of galactic history being written. Its first deep-field image was a stunning declaration of its power. It pointed at a patch of sky no larger than a grain of sand held at arm's length, a field Hubble had already observed. Where Hubble saw darkness and a few faint smudges, Webb saw a universe bursting at the seams. The image was crowded with spiral galaxies, glowing orbs, and chaotic infant galaxies, their light having traveled for over 13 billion years to reach us. But the real shock was not just the number of galaxies, it was their maturity. The models predicted that the first galaxies would be small, shapeless blobs, mere building blocks slowly merging over eons. Instead, Webb found galaxies that were already massive, large, and surprisingly structured, with distinct disks and spiral arms, when the universe was only a few 100 million years old. It was like opening a family album expecting to find a picture of a toddler, and instead discovering a fully grown adult. These precocious galaxies are forcing a dramatic rewrite of our theories of galaxy formation, suggesting that the early universe assembled its largest structures with a speed and efficiency we do not yet understand. Beyond the primordial galaxies, Webb has turned its infrared gaze toward the atmospheres of distant exoplanets. As a planet transits in front of its star, a tiny fraction of the starlight filters through its atmosphere. Webb's sensitive spectrographs can break this faint light into a rainbow, reading the chemical fingerprints imprinted upon it. It has already detected the clear signatures of water vapor, carbon dioxide, and methane in the skies of gas giants hundreds of light years away. For the first time, we are not just finding these worlds, we are beginning to taste their air, to analyze their chemistry from across the galaxy. This is the crucial first step in the long search for biosignatures, the atmospheric clues that might one day hint at the presence of life. Closer to home, Webb has pierced through the thick, opaque dust clouds that hide stellar nurseries. We can now witness the violent, beautiful process of star birth in vivid detail, seeing newborn stars igniting within their dusty cradles and the intricate structures of the gas that will one day coalesce into new planets. The James Webb Space Telescope is more than an observatory. It is a revolution in perception. It is challenging our fundamental stories of cosmic evolution while simultaneously providing the tools to write the next chapters, from the birth of the first galaxies to the potential for life on worlds beyond our own. If our very first deep look back in time has already upended our expectations, what other foundational truths about the cosmos will we have to abandon as this golden eye continues to peer into the deep past? For billions of years, the solar system has been a shooting gallery, with Earth a silent target in a cosmic crossfire. The DART mission was our first attempt to fire back. On September 26, 2022, a refrigerator-sized spacecraft named DART closed in on a tiny, distant world called Dimorphos, a moonlet orbiting the larger asteroid Didymos. This was no flyby or sample collection. It was a planned, high-speed suicide run. With no brakes and no second chances, DART steered itself directly into the asteroid at over 14,000 miles per hour, transmitting its final, detailed view of the rocky surface until the moment of impact. The screen went black. Success was not measured in the flash of the collision, but in the subtle change it would create in the void. The goal was not to destroy Dimorphos, but to give it a precise, measurable nudge. Astronomers across the globe turned their telescopes toward the distant pair, watching for a tiny fluctuation in the rhythmic dimming of light that occurred as the small moon passed in front of its parent asteroid. Weeks of careful observation confirmed what the team had hoped. The impact had worked. DART kinetic punch had significantly altered the moonlet's trajectory, shortening its 11-hour and 55-minute orbit by 32 minutes. This was not a random shove. It was a predictable, calculated deflection, proving that with enough warning, we could use a spacecraft's own momentum to change the path of a celestial object. This first-ever full-scale planetary defense test transformed a theoretical concept into a proven capability. We are no longer passive residents of a solar system where asteroid impacts are an unavoidable act of fate. We have demonstrated that through human ingenuity and precise engineering, we can actively defend our planet, turning a dire threat from science fiction into a manageable problem of orbital mechanics. The mission's success marks a profound shift in our relationship with the cosmos, from one of vulnerability to one of empowered guardianship. If we can successfully alter the orbit of a distant asteroid, what other cosmic challenges, once thought insurmountable, might we one day learn to navigate?